Welcome to lesson 4 of module 2, where we will be going into unsymmetrical faults. Although I did not put this as part of your module 2 notes, I thought I should just give you a very high level so that you can be assisted in looking for your information for your assignment. So we first define a short circuit. We always hear about short circuits happening in our networks, and it's actually a fault where you've got large current flowing in one or more of your phases, and therefore it reduces your voltage to zero at the point where your fault is. They occur in our power systems when equipment insulation fails, and I've already explained in module 1 how our equipment insulation gets to fail. So your short circuits will occur as either your single line to ground, your line to line, or your double line to ground, or it can be a balanced three-phase fault. Don't forget that you could also have an open circuit that can happen in your line where you have either one or two of them happening in a system. So your path of your fault current may have either a zero impedance, which is called a bolted short circuit. When we have a balanced three-phase system and you have a fault that occurs on all your three phases, we only experience a positive phase sequence, okay? So your zero, positive, and negative phase sequence are completely uncoupled. They only occur when you have an unsymmetrical fault on your system. Otherwise, if there is no such fault, then they do not exist in your system at all. So in this chapter, we are going to looking at our three-phase systems where we have unsymmetrical faults, and we're going to see what really happens when our network split into your zero, positive, and negative. I'll mainly really concentrate on the zero because on your positive, I'll show you how we can do it, and then you just need to put in a generation source, and your negative is usually drawn just like your positive, except it doesn't have that generation source. So there's assumptions that we are going to make. And the first one is that your power system operates under balanced steady state conditions before a fault occurs. So you actually do have a system that is in operation. And so before that occurs, you know that then our symmetrical components are uncoupled, they do not exist. So during your fault, that's where they get interconnected at only on that fault location that you have. We assume that we have a pre-fault load current, which we neglect, and that our pre-fault voltage is usually called VF. So for our positive sequence, we usually draw in our VF onto our bus bar. Your transformer winding resistance and shunt admittance are usually transmission line series resistance and shunt admittances, we neglect them. Your synchronous machine armature resistance and salient saturation, we neglect. All non-rotating impedances are neglected. Then for induction motors, we either neglect them or represented in the same manner as our synchronous machines. Now we look at conversion of our systems into a per unit system. So firstly, our per unit system, we do calculations in the power system analysis using them where we replace your voltage, your current, your impedance, and your power with whatever is the reference base voltage on them. Then for our network reduction, we usually have our complex notation. We utilize Kirchhoff's first and second law. We can do a delta to star conversion so that we make our circuit simpler. We then utilize Thevenin's theorem where we are simplifying or reducing the circuit. We've got Norton's theorems. We've got a combination of your parallel branches and equal driving voltages. You have your common voltage base that we need to put in, and then that basically gives us a summation of what our per unit system would look like. So on my top right hand side, I've shown you various formulas that we have or that we utilize in order to change your impedance into a per unit, a new per unit system, and you're even calculating your fault current. Then I just want to state here that the NB stands for your new base. The GB is your given base. So if they give you anything in per unit, you must know that it was your given base. And as long as you are given some base values, you must change into your new base. Then we've got for your base conversion, that is at the bottom of my slide on the right hand side, where I'm explaining that the GB is your given base and the NB is your new base. And then I'm showing you what your Z per unit can be on your new base, where you times is equal to your given base multiplied by your S new base over S given base multiplied by your V given base squared over your V new base squared, which can also be seen as your S base over your S actual. So I've just given us a very simple system where I want us to practice converting into a per unit. Now you're given a network where you've got 3 generators, 3 transformers, and 3 transmission lines in it. And you are given what their MVA ratings are, and then for your lines you are given what their impedances are. So if we start with the generators, you can see that for my G1, I say that it's going to be my given XPU. I multiply by my S new base over my S given base. My S new base is the 15 MVA that they say I must use as S base, whereas my given base, you can see from there what I was given that it was also 15 MVA in this case. So the XPU is that X percentage was equal to 15%, which is in per unit just becomes 0.15. There I do that multiplication and I can get the answer. Look at generator 2, you do the same thing. The difference now is that my given base was 10 MVA, so it would be 15 over 10. And my X percentage was 10%, so that's 0.1 in per unit. And then for my Gen 3, you can see also that my given base was 10 MVA, so it becomes 15 over 10, and I multiply that by my 12%, which is 0.12 in per unit. So I've got all my new base values for my generators. Then I go into my transformers, and then for my transformers, you can see that I've got the first transformer was 4%, which is 0.04 per unit, and it's 10 MVA for given base, so I multiply by 15 divided by 10. And then for your all your transformers are 10 MVA, so they're all going to be multiplied by 15 over 10. And then for your second transformer, it was 6%, that's 0.06. And for your third transformer, it was 7%, which is 0.07. Then I can be able to get all my new per units. Then the last part that you do is your lines, and for your lines, you utilize the formula that said Z actual multiplied by your SB divided by your VB squared. All right, so I've got my Z actual, which is the impedance that they've given me. I multiplied my S is going to be that base that they say I must utilize, which is 15 MVA. And then for the voltage, where do I get it from? Well, in this system, it's a 132 kV system on my bus bars. So that's why I've got the 132 that I'm utilizing. And then I'll be able to calculate for all my 3 lines. So now you can see now I'm going further into the question by saying, now that I've got all my per units, I want you to calculate the total fault current if you have a 3-phase fault developing on my 132 kV bus bar at station A. Please note where I have thrown in my station A and how I'm showing that there is a fault in there. So therefore, what I do is I first do my delta conversion in order to simplify the circuit. And I do that by doing that formula that says ZAN, ZBN, and ZCN. Once I've done that, then I start reducing my network towards the fault, which is my A bus. So I try to add on all of my impedances that I can add together. And you can see I've got a Z100, which consists of my furthest line at the bottom that was happening over there, where I had ZBN, XX2, and G2. Then I had my Z200 that I put together, which was the bottom part where I had the transformer 3 information. Then I had my Z300 where it was going towards bus 1 and I had generator 1 and transformer 1 in it. I can then reduce the network even further and I draw it out for you so that you can see after I've done this, this is what I now get. And then I can reduce it further now from this point because you can see that my Z100 and Z200 are actually in parallel. So I can do the parallel calculation and then I will add on my ZAN and I end up with something I can call my Z400 now. Now that I've got those two, I can see that my bus A is there where my fault occurs, then that means that these two impedances are actually in parallel. So therefore, I can then work out my Z per unit Thevenin equivalent of the parallel 2, and then my I fault simply I go and substitute into the formula that says SB over square root of 3 VP times my Z per unit, which will be my total Thevenin Z per unit. So what we're looking at now was if we had a balance fault occurring. Now, this chapter, we're not dealing with that. We're dealing with unsymmetrical fault, which means they are not balanced. So for this type, that's where you're going to get your sequence networks coming in. So in any part of your network where voltage drop is caused by your current, it depends only on the impedance of that part of the network where the current is actually occurring. So for our positive and negative sequences, which is Z1 and Z2, they usually are equal, all right, unless they give you in the problem that X is they got different values in them. Then for your Z0 is generally different from your Z1 and Z2 totally. Then only your positive sequence circuits of rotating machines contain sources which are of positive sequence voltages. So even if your Z1 and your Z2 are the same, exactly the same, when you draw your positive phase sequence and your negative phase sequence, the difference between the two is that on your positive phase sequence, you will also put in your sources into them and actually draw them up. Neutral is the reference for your voltages in your positive and your negative phase sequence circuits. Whereas on your zero, you've got ground will be your physical connection into that. Then we say we don't have any positive or negative sequence current flow between our neutral points and ground. Your impedance of Zn, all right, which is the physical connection between your neutral and your ground point, are not included in your positive and negative sequence circuits. They only get introduced on your zero phase sequence and they are usually 3 times of that value. So this is our zero sequence networks. This was also shown on your previous lesson, but I thought let me just put it in here so that we can refresh our minds again. So for the first part is your Y to Y connections and they are both earthed and that is how they get represented on the right hand side. Then you've got your one of them is earthed and the other one is not earthed. So the earth side, you can see that there is a connection, but where the one without the earth, you can see that I've got an open point happening in the system. Then where you've got your Y connection unearthed to your delta connection, you can see that I draw in up until that point and then it's open where it goes to my delta connection. Then where I have an earthed Y connection and a delta connection, you can see that I come in from my star and I go down to my reference voltage and then for my delta it was an open circuit on it. Then where I've got a delta to delta, you can see I've open circuited on both sides and then I just show the transformer going down to earth on either side. So in this slide, I thought let me just bring in one or two examples where we're showing basically how you would draw your zero sequence network. So the first one, you've got a generator connecting into a transformer, two lines that are parallel, and then going through to another transformer feeding a motor. And at the bottom is how you would throw it in. You can see that the generator, there is no impedance going down to earth on it, so it's just the generator impedance that I'm putting in. And then you can see how your transformer is connected because it's a star to star, that is earth, and then my two lines and then going out. I'm not connecting back to my reference bar because that star connection for the motor was not earthed. Then if you look now on the second part of my system, you can see that I've got now a impedances from my generator sources. So therefore those get multiplied by 3, and then I just show what my generator normal impedance was going to be. And then I also show that from generator 1, I've got an open point because when I go into the transformer, I've got a delta scenario. That's why we open it when you come in. And then the other part will then, because it's earthed, I connect it to my reference bar. Thank you very much.